Okay, let's start with the next talk. It's by Dennis Howe, and he's talking about extensions of Rowland's prime generating sequence.
All right, so by way of disclaimer, I am pretty clearly the least qualified person to be speaking at this conference, so apologies in advance. And this talk is sort of a tribute to Doron Zeilberger's teaching ability. It's as important, if not more important, to pass on to the next generation as it is to do your own research. And this is true in two ways. One, because my paper is actually about Eric's dissertation topic, half of it at least. And two, because this work actually came out of the final project for the experimental math class that he taught this past semester. So there's that. All right, so we'll get started. So we define a sequence, let's say A1 equals 7, and AN is equal to AN minus 1 plus GCD of N, comma, AN minus 1. This was discovered in 2003 at the NKS summer school, Wolfram et al. And apparently, this generates prime numbers in some sense. Specifically, we define a function, Gn, to be this difference. So obviously, it's also equivalent to GCD. And it turns out that with initial condition 7, you get all ones or primes. And he actually proves this. I won't go into the details because we're going to try to extend this. So I guess the most notable contribution besides Eric's is Benoit. Cloitre has a kind of very similar looking thing. He actually starts with 1, but you do whatever. And what you do is LCM instead of GCD, instead of straight up subtracting, you divide, and then subtract 1. And this also appears to generate primes, although I don't think it's actually been proven because the guy he just writes these things in French to himself, and I think he's even lost interest, and he's not going to get back to it for another 3 years. So anyone can take a stab at this, but we'll get back to that. More on this first.
Sorry, who's that by?
So, I mean, the first few terms of this, so you got a bunch of 1s, and then interspersed you have some primes. And in fact, there is a nice way to skip the 1s, but it's equivalent to calculating really, really big factors. Like, I'm talking 10 to some mildly large 2-digit number, and factorizing that is a pain, but you end up getting these primes, and if you plot it, you sort of get these 2 fans. So you've got the really big ones over here, and then the small ones repeat. And it's conjectured by Eric, I'm not sure if it's proven, I don't think so, that this actually will get every prime. And to date, the smallest prime that doesn't get generated after 10 to the 30-something iterations or whatever is 587, if anyone wants to try to find that. So it's a nice shortcut, and as I said, you can read Eric's paper, and we'll get into that. All right, so I was sitting there thinking, okay, I'm going to be clever. Eric already has a list of open problems, but I'm clever, so I'm going to come up with my own open problems and try to solve them. Of course, that failed completely. So first, I was thinking, how can all right. So Eric's question was basically, is this thing part of some larger class of prime generating recurrences? So instead of dealing with that, I thought to myself, well, can we get more traction out of this? What else can this thing do? So of course I thought, well, what happens if I start with an initial condition that's a Gaussian prime? And it fails because, and you sort of see, you're dealing with an integer, so one problem is you end up with a constant times some Gaussian. But even if you get rid of that, I've been toying with a lot of different initial conditions and trying to stretch it out, and you still seem to get weird things happening because Gaussians are kind of odd. So that doesn't seem to work. Then another one that you could think of is irreducible polynomials. Is there some way we can generate those? And of course, there's something degree 0 there, so that's not going to work either. So that was stupid. And at this point, I realized this was the wrong approach and gave up and thought, well, is there some way we can tweak this so that it generates Gaussians or irreducible polynomials, or even, given some initial condition, numbers relatively prime to something? But I haven't found anything yet, so if you come up with anything, let me know. So this brings us to the slightly more fruitful part, where instead of looking just at that, trying to broaden it to a bigger class. And this is actually due to Luis Medina, I think he's here somewhere. This question: what happens if we replace n here with f of n? Of course, it's a really big question, so we're just going to do some simple cases to start off with. Case 1, stupid case. Instead of x, let's try constant times x. Why is this stupid? If you try calculating it for a little bit, you get a little trail, right? And then k just repeats. So, no good. Case 2, let's try, this is where it gets interesting. Let's try f of x is x squared. Here was the values. Now, otherwise, and I'm assuming initial value 7, but this actually does generalize to other initial values. We get this little chart, and try color code it. So this is for the nth iteration. X doesn't mean the value of x, it means what you get if you're using x instead of x squared. So don't be confused. These are the only differences, up to whatever n. So at 117, 13 switches to 116.